Welcome to The Explainer, where we break down complex topics using slides. Today, we are going to get into the nuts and bolts of flight control.
You know, it's a great question. You look out that window and it just seems impossible, right? But it really boils down to some core principles of physics and some seriously clever engineering.
So that's what we're going to do today. We're going to explore the incredible systems that give pilots precise control over this massive machine that's moving through three-dimensional space, all by using a few key surfaces on the wings and the tail.
See, flying isn't like driving a car where you just turn the wheel left or right. Up in the air, you're moving in 3 dimensions. So a pilot has to control the plane across 3 different axes of rotation.
And this table just lays it all out so perfectly. You've got 3 basic movements. First, there's pitch. That's the nose tilting up or down. Then you have roll, with the wings banking left or right. And finally, yaw, which is the nose swinging from side to side. And each one has its own special control surface.
All right, let's start with roll. This is all about the ailerons. So imagine the pilot pushes the stick left. What happens? Well, the left aileron flips up, which kills some lift on that wing, while the right one goes down, creating more lift. And that difference in force, that's what makes the plane bank and roll right into a turn. So cool.
Okay, so what about pitching the nose up and down? That's the job of the elevator way back on the tail. So when the pilot pulls back on the control yoke, the elevator flips up. This pushes the whole tail assembly down, which in turn points the nose up toward the sky. This is absolutely critical for climbing, for descending, and especially for that little flare right before you touch down for a landing.
And that brings us to our third movement, yaw. Now this one's controlled by the pilot's feet using the rudder pedals. You push the left pedal, the rudder on the tail fin deflects to the left, and it pushes the tail to the right. The result? The nose of the plane swings, or yaws, to the left. It's a lot like the rudder on a boat, really. Okay, so it all sounds pretty straightforward, right? Ailerons for roll, elevator for pitch, rudder for yaw. But this is where things get a little tricky, because in the world of aerodynamics, every action has a reaction, and sometimes it's one you really don't want.
The key thing to understand is what this quote is telling us. That aileron that goes down to create more lift, well, it also creates more drag. It's like it's dragging its foot through the air. And that extra drag causes something called adverse yaw. I mean, just think about how wild that is. The pilot moves the stick to turn left, but for a split second, the nose of the plane actually swings the wrong way, to the right. This makes for a really sloppy, inefficient turn. And for the early pioneers of flight, this was a massive, massive puzzle they had to solve.
And engineers being engineers came up with some brilliant fixes. This slide shows 2 of the best. With differential ailerons, the one going up moves a lot more than the one going down. This creates some extra drag on the upside to even things out. But freeze-type ailerons are even cooler, I think. They're hinged in a special way so that when the aileron goes up, its leading edge actually sticks down into the airflow, creating its own little pocket of drag. It's just elegant engineering.
So, they solved adverse yaw, but as planes got bigger and faster and heavier, a whole new problem cropped up. A human pilot, no matter how strong, just couldn't physically muscle these huge control surfaces around against the force of the wind. The systems just had to get smarter.
And you can really see that evolution laid out here. It started simple, right? Just a direct connection of cables and pulleys from the cockpit to the wings, pure muscle power. Then came hydromechanical systems, where hydraulic pressure did the heavy lifting for the pilot. And that brings us to today's big airliners, which use fly-by-wire. The pilot isn't physically connected at all. They're just telling a computer what they want to do. And the future? We're talking about intelligent flight control, systems that can literally relearn how to fly after taking damage. Incredible stuff.
But flying isn't just about turning and climbing. There's a lot more to it. Pilots need ways to fine-tune the flight, especially for critical moments like takeoff and landing. And for those long-haul flights, they need something to fight off exhaustion. And that's where these secondary controls come into play. Think of them as the fine-tuning knobs. You've got flaps, which basically change the shape of the wing to give you more lift at slow speeds. Spoilers do the exact opposite. They spoil the lift, helping the plane descend faster or act as brakes on the runway. But the most important one for the pilot's sanity? That would be the trim systems. Trim is without a doubt a pilot's best friend. What it does is it lets you set the controls so the plane wants to fly straight and level all by itself. So instead of constantly having to push or pull on the yoke to hold your altitude, you just dial in the trim and the aerodynamic forces do the work for you. You can literally take your hands off the controls.
It's a total game changer for reducing pilot workload on long flights.
Okay, so we've gone from muscle power to hydraulic help to computers. The final step in this evolution, well, it's handing over a big chunk of the workload entirely to a machine.
So when we talk about a modern autopilot, how much can it actually do? How many of those axes of flight can it handle? The answer is all three. A standard three-axis autopilot can control the roll with the ailerons, the pitch with the elevator, and even the yaw with the rudder. It uses gyroscopes and navigation data to fly the plane completely on its own.
When you think about it, the journey has been incredible. We went from early pilots wrestling with unstable machines to today's highly integrated systems. The autopilot isn't just a gadget, it's the culmination of more than 100 years of innovation, all designed to make flying safer and more efficient.
And all this progress leads us to one final really interesting question for the future. As these flight computers get smarter and smarter, so smart that they might even be able to handle major in-flight emergencies all by themselves, what does that mean for the role of the human pilot in the cockpit? It really makes you wonder what comes next, doesn't it?